Okay, how are we doing for time? I think I'm going really slowly. I'm going really slowly, but this was the question that hits all the major topics. So finally, how many bytes of data does how many bytes per second? How many bytes per second of data does the oscilloscope produce? Right. So this is the final kind of question where you put together your sampling rate and your quantization, your number of bits in quantization to get an answer. So the technique that is very good to use here, I'll write directly on the paper since we have more space. We want to know how many bytes are created in 1 second. Right? So 1 second is what we know. So let's write down 1 second. And we'll take a number of steps to convert this 1 second into the units of bytes. Okay, so seconds can be converted into samples by using the sampling rate. Right? So we had a sampling rate of 2 megahertz. So that means 1 second can be multiplied by 2 times 10 to the 6 samples divided by 1 second. Okay, is that clear to everyone? This fraction over here is equal to 1 because we have 2 million samples every second. Okay, so I'm just taking a number and multiplying it by 1, and I get to change the units in this way. So now our whole expression here is in terms of samples. I can convert samples into bits because every sample is quantized to 12 bits. That was provided in the previous part of the question. So I want to divide through by samples. And so what I can write is that every one sample comprises 12 bits. Right? So now we're getting, our whole expression is getting much closer to the answer that we want, which is bytes. So there's only one thing to do, is to convert bits into bytes. So the relationship here is that 1 byte is equal to 8 bits. Right? And so now it's complete, in fact. So we can, we can cancel out all the units, and we have an answer in bytes. So we multiply these together. So explicitly, this is 1 times 2 to the 10, 2 times 10 to the 6 times 12 times 1/8 is our answer in bytes, which works out to be 3 million bytes. Okay? So the answer is 3 million bytes per second of data. Okay, so that is sort of the full gamut of sampling and quantization questions. I mean, the very standard sampling and quantization questions. I think what was most difficult is clearly the alias frequencies. So maybe there are a couple more questions on the very last page of the packet that deal with alias frequencies, and perhaps we can come back to those at the end, so that we can hit some other topics. Yes.
In part A, you said that there was no aliasing going on. We checked parts that said no aliasing. Then how come in part E that we find 3 aliasing frequencies?
Let's check the wording of the question. That is confusing wording. So initially, one sinusoid was given and 1 sampling rate was given, and because the sampling rate was more than twice the frequency of the sinusoid, this frequency is not aliased, right? That's what this is saying. And now I've lost, where's that page? There it is. In this part of the question, it says, find some other frequencies that do alias, but they alias to the same frequency that we just saw, right? So if I were to draw them over here, they turn out to be higher frequencies. They're not at 0.833 megahertz. One of them is, the next one is at 1.167. So the picture that I would draw would, the sinusoid would oscillate much more frequently than this. But interestingly, the whole point is that it would oscillate in such a way that it hit all of those square points, right? It wouldn't be the same curve. It would go up and down much quicker, but it would somehow hit all of those black squares, right? So it's ambiguous. If you just have those black squares, it's ambiguous which of those the original signal was. The way that the reconstruction works in the D to A is that it picks the lowest frequency that makes sense, which is the one that's drawn, right? So that's why all the other ones are set to alias onto this one.
When we drew that sawtooth, does that diagram depict the sampling frequency? Is that why?
Okay, this sawtooth, now I've kind of drawn over it with a lot of other stuff, but the sawtooth function is, it goes up and down as a sawtooth does, and it touches down at f sub s. That's the first place it touches down in the square box here is f sub s, the sampling frequency, right? So if you know the sampling frequency, you can draw that. You can write that. I've written 2 megahertz right here, right? And that kind of tells you, where it touches down and exactly how the f-axis works relative to that sawtooth. And it also tells you how high the sawtooth goes on the g-axis, right? So if you know that sampling frequency, you pretty much know everything about that curve. Yes.
Frequency, when does aliasing? In terms of frequency,
Yeah.
when does aliasing?
So aliasing occurs at, you can see that in this curve, in this graph, as long as f is between 0 and fs divided by 2, it just maps to its same value, because that line is the y equals x line, right? That maps any value to itself. So no aliasing happens here. No aliasing happens there. And then for any higher value of f above fs divided by 2, right? Then you're off that curve which continues up in that direction. You're off that curve, so your g is no longer equal to f all the way here. So let's now connect what I was just saying to Nyquist sampling, right? As long as if f is less than fs divided by 2, then no aliasing happens, right? Which is the same thing as saying that fs is greater than 2f, right? Which is f Nyquist. And I just did some manipulation of the symbols to turn this into this, and this was our statement before. Where did I write it? I wrote it back here. Fs has to be greater than 2f, and right there, fs has to be greater than 2f. Right? So that property is captured in the picture as well as basically the first kink in the sawtooth, where it starts going down instead of continuing up. Yes.
If any frequency, let's see, that's like right above the Nyquist rate. Okay. Any frequency like more than half. I can't think of how I'm saying this, but why is that one the first frequency that produced an alias? If twice the frequency is a Nyquist rate, right? So, like, if our frequency is 2 millihertz or megahertz, then wouldn't one right after 1 megahertz produce an alias, or why?
You said it right. Our sampling frequency is 2 megahertz, right here, right? That means this fs divided by 2 is 1 megahertz, as I've drawn right here. So when f goes above fs divided by 2, then it's no longer on the, you know, on the curve, on this curve that goes up like that. It's on this downward part of the curve, and so it maps to a g, which is not equal to itself. It maps to a lower value of g. So yeah, what you said is exactly right. If the sampling frequency is 2 megahertz, then if f goes above 1 megahertz, half of it, then it aliases to something else. Right? Sometimes we say, you know, it might be confusing because I said, you know, the sampling rate has to be twice the frequency. Right? The sampling frequency has to be twice the maximum frequency. But the other way of saying that is that the maximum frequency has to be less than half of the sampling rate. Right? So it's the same thing, it's just a different way of writing that inequality. Okay, yeah.
So